Dr. Andrew Siemion is an astrophysicist at the University of California, Berkeley. He serves as the director for the UC Berkeley Center for the Search for Extraterrestrial Intelligence Research. He's jointly affiliated with the Netherlands Institute for Radio Astronomy and the SETI Institute in Mountain View, California. He's a serious scientist who is undertaking, trying to get us some data to answer one of the biggest questions that's out there: are we alone in the universe? And I personally am excited to hear what the latest on that research is. So please join me in welcoming Dr. Siemion. Thank you very much for being here.
Thank you. I think I'd like to start with a video, please.
Pick a star. Any one of the hundreds of billions of stars in our Milky Way galaxy. Suppose on one of its planets there lives an intelligent species who believes that their world is the center of the universe. A universe made for them. We awakened on this tiny world beneath the blanket of stars without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last 6 years, we have discovered nearly 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are there any on which matter and energy have become alive or aware? Are we alone? If we are, then that tells us something about the preciousness of life on Earth. And if we're not alone, then what discovery could possibly be more important? It's time for a major international effort to unlock the great unanswered mystery of life in the universe. We have only just begun to open our eyes. Come with us.
I hope you enjoyed that video. That was put together by Annie Druyan. And if you don't know who Annie is, she's Carl Sagan's widow and was his partner both in his life and his work. And it was narrated by Seth MacFarlane. And that video was shown a couple of years ago for the first time at the announcement of the Breakthrough Initiatives at the Royal Society in London. And the Breakthrough Initiatives is a series of scientific programs asking the question, are we alone? Pondering the possibility of life in the universe, of which Breakthrough Listen the SETI effort that I'm going to speak with you about is one. I wanted to start with thanking Les for that wonderful introduction, and everybody at the Tennessee Valley Interstellar Workshop for having me here. It's really a wonderful privilege to come to the workshop, which I've read so much about, which I've told a number of people that I've read quite a lot about it. So it's wonderful to see it in person. And it's also my first time in Alabama, and obviously my first time in Huntsville. So wonderful to be here. And I'd like to especially thank Jim Benford with Starship Century, who actually was the person who initially invited me to attend. We know from images like these, this is just a part, something called the Hubble Deep Field. It's one of the deepest images that we've ever taken of the night sky. It's just a few arc minutes on a side. And every little point of light that you see here is actually a galaxy. And we know from images like these that there are something like several 100 billion galaxies just in the part of the universe that we can see, the so-called visible universe. And each one of these galaxies has something like a few 100 billion stars in it. So really an incredible amount of real estate out there. The universe is bigger than I think many of us can even imagine, certainly than I can imagine. And ever since the dawn of humanity, we've gazed up at the night sky, of course not always like with images like this until very recently, and asked the question, is there anyone else out there? Is there anyone out there that we could potentially communicate with? Is there anyone out there maybe looking back at us, thinking and asking the same questions that we're asking about space? At the beginning of this century, or the last century, in the last 100 years, some of the very first experiments were done to try to answer this question. And this is a picture of an astronomer, a gentleman named Professor David Todd, and an electrical engineer, a communications engineer, named Charles Francis Jenkins. And they're examining a device called a radio photo message machine. It's an early version of a television, really. It was a device that Charles Francis Jenkins had himself invented. And these two got together and decided that it might be an interesting idea to take this device and hook it up to the largest antenna that they could find and point it at Mars at the time of closest approach between the Earth and Mars. So when Mars was as close to the Earth as it could possibly be. And one of those times occurred in August of 1924. So they put this gadget together, and they were very smart. They knew that even then, that the radio technology that we had on this planet could potentially interfere with their experiment. So they went so far as to ask the U.S. government to suspend all radio traffic, all radio communication, all radio activity during a set period when they were going to conduct this experiment. And they carried out the experiment, and they even took some data. And here's an image from the radio photo message continuous transmission machine from August 22nd to 23rd of 1924. And I'm not 100% sure of this, but I think that the axes here are something like frequency here and time in this direction. So this is an exposure of an image that they took with this early radio receiver. And as we'll talk about more as the talk goes on, this is really not dissimilar in principle from the way that we conduct searches for extraterrestrial intelligence today. But there was one very big problem with this experiment that most of the radio communication engineers in the audience will immediately recognize when I tell you that they observed at about 50 kilohertz. And unfortunately, that radio frequency is too low to penetrate the Earth's ionosphere. So there was no way that they would ever detect any radio transmissions from beyond the Earth. And of course, now we know that there isn't any intelligent life on Mars. But it was a fantastic early effort at trying to answer this question. The scientific search took a big step forward in a number of ways in the late 1950s. First with a paper that was published in the journal Nature by Giuseppe Cocconi and Philip Morrison called Searching for Interstellar Communications. This was the first paper that really laid the groundwork for the way that we conduct SETI today. It identified gigahertz radio frequencies as the ideal part of the radio spectrum to search for these signals. And very importantly, it showed that these kinds of signals could reach interstellar space. that they could traverse the very, very large distances between stars. Amazingly, just a couple of years later, Charles Townes and Robert Schwartz, a student of his, published a similar paper, also in the journal Nature, entitled Interstellar and Interplanetary Communication by Optical Masers. So some of you might be asking, well, what's an optical maser? Well, that's what they called lasers before they called them lasers. And in fact, Charles Townes won the Nobel Prize eventually for the discovery of lasers. Around the same time, and independently, a young astronomer named Frank Drake, who was newly stationed at the National Radio Astronomy Observatory in West Virginia, decided that maybe he would take one of their radio telescopes that had just been built and try to conduct a search at just these frequencies. And he did exactly that. He called the program Project Ozma, and he had only a single 100 hertz manually tuned radio channel. He literally had a headset and a radio that he could tune around a 400 kilohertz band around a center frequency of 1420 megahertz. So 400 kilohertz, that's 400,000 cycles per second. That's about the width of 2 FM radio stations. And that's all that Frank could search at the time. But again, as we'll see as the talk goes along, this is really the very pioneering work that laid the foundation for everything that was to come, including what we're doing now with Breakthrough Listen. In response to all of this flurry of activity, a conference was convened at the National Radio Astronomy Observatory in West Virginia. And a number of the most famous scientists in the world were invited to attend. Melvin Calvin was there, who's a very famous chemist, who actually received notification that he would win the Nobel Prize for his work on photosynthesis while he was at this meeting in 1961. Also there was Otto Struve, one of the most famous astronomers of his day. John Lilly, who, as some of you may know, was very famous for his work with dolphin communication. And actually this group that gathered at the National Radio Astronomy Observatory coined themselves the Order of the Dolphin in honor of John Lilly. Also there was Carl Sagan, then very young and just a recently minted PhD graduate. And of course Frank Drake himself was there. And it was actually at this meeting that Frank Drake first suggested this equation, an equation now that is nearly as famous, I think, as E equals mc squared, the Drake equation, where he expressed n, the number of civilizations that we might be able to communicate with, as the product of a number of factors. The rate of star formation in the galaxy, the fraction of those stars that have planets, the average number of planets that are Earth-like, and so on. And this was never sort of imagined to be an analytical expression for how to detect the number of civilizations that we could detect. Rather, it was a thought experiment. But I think it bears mentioning that when this equation was suggested, the only one of these terms that we had any idea what the value was our star, the rate of star formation in the galaxy. We had a pretty good idea that was about 1. But the fraction of those stars that had planets and all of these other terms, we had absolutely no idea. Well, in the last 60 years, things have changed remarkably. So we now know that virtually every star in our galaxy has a planetary system. And a good fraction of those have a planet that exists in what's called the habitable zone around the star, the distance to the star where liquid water could exist on the surface of the planet. 1 in 5, 20%. We've also learned amazing things about life on our own planet. This is something called a black smoker. It's a hydrothermal vent far down in the ocean, several miles beneath the surface of the ocean. This particular one is in the Marianas Trench. And it was discovered that these black smokers, these hydrothermal vents, are actually home to entire ecosystems of life that exist completely independently from sunlight. In fact, the ecosystems here in these hydrothermal vents are driven by chemosynthetic bacteria, a life form that actually gathers its energy from chemical reactions around the hydrothermal vent. A truly amazing discovery that shows how life can exist in really extreme environments. And it's caused us to begin asking questions about the habitable zone itself. Is it really necessary for liquid water to exist on the surface of a rocky planet for there to be life in an environment? Could perhaps there be life in a liquid ocean beneath the surface of one of the moons of Jupiter, or maybe Saturn, where the water is kept in a liquid state not by sunlight, but by gravitational forces, the tugging of the moon against the planet, and vice versa. We also learned that life began extremely quickly on this planet. Essentially, as soon as the Earth was cool enough for life to emerge and thrive, it did. And these are colonies of bacteria called stromatolites. And we've discovered these stromatolites in Western Australia that date to just a few 100 million years after the formation of life on Earth. And of course, as evidenced by all of us here in this room, life went on to develop an extraordinary amount of complexity and indeed technology. But the question remains, has life developed on any of those other worlds? Worlds that we know are out there, worlds that we know are bathed in water, worlds that we know have ubiquitous organic chemistry, all of the conditions that are necessary for life to arise on one of those other worlds exists, but did it remains an open question. And I think even more of a pointed question, I think as human beings, we ask ourselves, could any of that life have developed intelligence? Could any of that life have developed a technological capacity similar to what we have here on Earth? And perhaps could they be thinking and communicating and asking the same questions that we are about them, about us? As you might expect, the search for life is a huge topic in science. There are literally hundreds of astronomers and engineers, scientists of all stripes, that are seeking to answer this question. And when we think about detectable signatures of life, there are really two methods that receive the most attention, certainly in the scientific community. One is what we call in situ sampling. That's where we send a craft of some kind, a lander or an orbiter, to an environment that we think might have life, usually within our solar system. And we directly sample that environment to see if we see any evidence of biology. And this is the ESA, European Space Agency, ExoMars 2020 rover, which is going to do a fantastic job of that on Mars here in a few years. Another idea, which just recently has become very exciting, is to look at the atmospheres of these extrasolar planets that we're discovering. So if we observe the planet as it passes in front of the star, we can do something called solar occultation or sun occultation spectroscopy. We can look at the light from the star as it passes through the atmosphere of the extrasolar planet, the distant planet around another star, and we can look at its spectrum, and we can study the chemistry of that atmosphere, and we can see if anything exists that we call disequilibrium chemistry. Is there some kind of chemical environment going on in that atmosphere that we wouldn't expect from natural processes? Is there something biological going on? But there's a key drawback to both of these techniques that might not be immediately obvious, certainly not immediately obvious with this technique. And that's that both of these are severely limited in their range. Even with the most ambitious projects, indeed the projects being discussed here at the Tennessee Valley Interstellar Workshop, we're probably only going to be able to do this within our solar system or maybe a few nearby stars. And remember, there's hundreds of billions of stars in our galaxy. Now, you might think that spectroscopic signatures, looking at the atmospheres of extrasolar planets, would get us out farther. You'd be right. But only a few dozen light years. And that measurement that I told you about, where you look at a planet as it passes in front of the star, is a very, very difficult measurement to make. And probably only a few dozen exoplanets, extrasolar planets, might be amenable to such a technique in the next couple of decades with the instruments that we have available to us now. But there is another way of searching for life, and as you might have already guessed, it's the type of search for life that I'm going to talk with you about today. For the last 100 years or so, our civilization has produced technology that emits signals, electromagnetic radiation, that could be detectable at interstellar distances if another civilization had observing facilities similar to what we have here on Earth. And that includes things like radio transmitters like this. This is the Sutro Tower in San Francisco, near where I live. Very powerful radar systems that are used for imaging the surfaces of asteroids and other planets within our solar system. And even high-power lasers. So ground to space, laser communication, these kinds of things. This is something that we're not yet doing a lot of. But with a thought experiment, if you imagine just taking the largest laser that we have here on this planet and the largest optical reflector that we have, the largest telescope, and you pair those, these signals would be detectable at thousands of light years away from the Earth. So in SETI, what we do is we turn this around and we imagine, well, suppose there's another civilization out there and they've developed technology, something like what we have here on this planet. Could we detect it? And indeed, we could. And we want to search for as many different types of signals as possible. So this is a plot of atmospheric opacity versus wavelength. Most of astronomy is conducted on the ground. And so this basically shows us what portions of the electromagnetic spectrum come through the Earth's atmosphere and the Earth's ionosphere. And as you can see, there's a very broad window here in the radio and other windows in the infrared and the optical. And we want to search for as many different types of signals as we can, so we want to search as many different wavelengths as we can, and that means using a number of different types of telescopes. So just as kind of a thought experiment, this is something that we're fond of doing in SETI. We can imagine taking our most powerful radio transmitter, which is the Arecibo planetary radar. So some of you may know that Arecibo is a telescope. It actually has a very powerful radio transmitter attached to it as well. A million watts, a megawatt transmitter. And this is a planetary radar. Again, it's used to make images of asteroids and planetary surfaces. And under the right conditions, a transmitter of this luminosity, or this equivalently isotropically radiated power for the RF engineers in the audience, a transmitter like this would be detectable across the galaxy. So while those methods that I talked with you about earlier can probe only a fraction of the galaxy, with our SETI searches, we're really only limited by the power of the transmitter. And with a transmitter just as powerful as the ones that we have on Earth now, and in fact one that we had on Earth several decades ago, we're sensitive to transmitters across the entire galaxy. And these experiments ask a very specific question. I think a more pointed question than just general searches for life. They ask, is intelligence a common outcome? So most people would accept, perhaps, that basic life could be common in the galaxy. There could be lots of single-cell organisms, lots of bacteria on the exoplanets that we've already talked about. But is intelligence a common outcome of evolution? Is intelligence and a technological capacity simply an evolutionary fluke here on Earth? Or is it something that a lot of life eventually evolves? And this is the question that SETI experiments ask. And indeed, it's a very special time in the history of humanity. It's the first time that we've known definitively that the possibilities for life are as great as they are. And it's the first time that we've had the capacity to actually search for intelligent life at interstellar distances. And this is something that was realized in a very significant way with the announcement of the breakthrough initiatives. Again, a series of initiatives centered on answering this question, are we alone? Is there other life of any kind elsewhere in the universe? Again, this was announced in July of 2015 at the Royal Society in London. The principal sponsor of the initiatives is Yuri Milner. He's a venture capitalist from Silicon Valley. And he was joined at the announcement by Stephen Hawking, Martin Rees, the Astronomer Royal of the United Kingdom. Here's Frank Drake and Annie Druyan. And the announcement of the initiatives was accompanied by a call to action of sorts. A full-page ad was taken out in a number of major newspapers asking the entire world to get involved in answering what is really our most profound question. The first of the initiatives that was announced was Breakthrough Listen. Of course, that's the program that I'm here to talk with you about tonight. Breakthrough Listen is a 10-year, $100 million program to conduct the most comprehensive, sensitive, and intensive search for intelligent life beyond the Earth in history. This is something that, again, has been going on for 60 years, but Breakthrough Listen is a giant leap ahead in our capabilities. We're going to survey 1 million stars, about 10,000 times more stars than have ever been observed before in a SETI program. Conduct a complete survey of our Milky Way galactic plane, the plane of our own galaxy, and also search a number of nearby galaxies to look for very, very bright transmitters. 1 day of the Breakthrough Listen program is equal to 1 year of any previous search that's ever been conducted. And the main reason that we're able to do that is because computers have gotten so much faster in the last couple of decades. SETI is unique in astronomy in that the power of our experiments, especially in radio SETI, are directly coupled to the speed of our computers. So as our computers get 10 times faster, our experiments get 10 times more powerful. And a very special thing about all of the breakthrough initiatives, but especially Breakthrough Listen, is that all of the scientific data gathered by the experiment is being made public. And not just the data, all of the instrument designs, all of the software that we write, everything about the program is in the public domain. We've announced so far 3 facilities that we've contracted time on, and I'll go through these in some detail. The Automated Planet Finder, an optical telescope, and 2 radio telescopes. The first is the Green Bank Telescope. This is at the National Radio Astronomy Observatory in West Virginia, the same site, in fact, where Frank Drake conducted that very first SETI search in 1961. But this is a brand new telescope. It's only about 15 years old. It has a fantastic surface accuracy, which means that it can observe to very, very high radio frequencies. In fact, this telescope can observe up to 100 gigahertz. That's 100 times higher in frequency than Frank Drake's very first search. And importantly, it can deliver a huge amount of this radio bandwidth to our instruments, up to 10 gigahertz of bandwidth. That's 10 billion radio channels. We've also contracted time on the Parkes telescope in Australia. This is a 64-meter facility, and it has a very special radio receiver that allows it to look at a huge amount of sky at once. It actually has a radio receiver with 13 separate beams on the sky, and this will be a key facility in conducting our galactic plane survey. And also an optical telescope. This is a telescope that we use to look for laser signals. This is at Lick Observatory near San Jose in California. And we've contracted 36 nights a year on this facility, 10% of the time on the telescope. And it has a very special spectrograph that was actually built to look for extrasolar planets and characterize extrasolar planets. But that same spectrograph has such high spectral precision that we can use it to look for artificially narrow laser emission. And that's exactly the role that it plays in the LISTEN program. We also have announced 2 partner facilities. These are observatories that we've not contracted time on, but that we're working together with to conduct observations, share software, and share technology. One is a brand new telescope that's just been built in southern China. It's called FAST. It looks something like Arecibo, and in fact it's built in a very similar geology. This area of southern China has what are called karst, or limestone depressions, just like Puerto Rico does. Except the FAST telescope is 500 meters in diameter, whereas Arecibo is 300 meters. So it's something like 5 to 6 times as sensitive as Arecibo. We've also contracted or signed an agreement with the Jodrell Bank Observatory at the University of Manchester. This is the 65-meter Lovell telescope. This is a very large radio telescope in the United Kingdom. In fact, the largest radio telescope in the United Kingdom. But Jodrell Bank Observatory is actually the headquarters for a brand new telescope called the Square Kilometer Array, which I'm going to talk with you about as we move forward. Another one of our partners is SETI at Home. Has anybody here run the SETI at Home screensaver? Great, thank you. So SETI at Home is what we call a distributed computing application. It's a program that you can download from our website, and when you download it and start it up on your computer, it waits until you're not doing anything with your computer, and then it connects to our computers. It downloads a little bit of data that we collect from one of these telescopes, and it does a very computationally intensive form of processing using your computer, and then it takes the results and sends it back to us and your results are combined with tens of thousands of other people that are running the same program, and allows us to look very, very carefully at small parts of the radio spectrum. And again, there are tens of thousands of people that participate in this. If you're not participating, please do. You can actually run this program on your cell phone now, as long as you have an Android phone. The iOS one is in the works. There are participants all over the world participating in this, and you can download data from all of the Breakthrough Listen facilities. I already mentioned the Square Kilometer Array. Again, this is an international effort to build a next-generation radio telescope. And a precursor to this telescope is being built in South Africa. It's called Meerkat. Eventually, there's going to be 64 of these 13.5-meter antennas. And this telescope will be the most sensitive and powerful radio facility in the Southern Hemisphere. And we're very close to announcing a partnership with SKA South Africa to add a SETI instrumentation capability to this telescope. And again, these are precursors to something called the Square Kilometer Array. This is a computer animation of what the Karoo Desert in South Africa might look like with many thousands of those antennas that I just showed you. And a square kilometer of collecting area is a very interesting number. It's about 20 times as sensitive as our most sensitive radio telescopes that we have now. But importantly, this would be the first telescope that would be sensitive to what we call leakage radiation. So oftentimes in the kind of cartoon picture of the search for extraterrestrial intelligence, we talk about detecting I Love Lucy television transmissions. The truth is that those isotropic transmissions are too weak for us to detect with our generation of experiments we're running now. But with the Square Kilometer Array, we could detect them. And we're very excited about being a part of this telescope with the Breakthrough Listen program. And the kinds of SETI that we do on these array-based telescopes is very different than the kind that we do on single-dish facilities. In fact, we can use these telescopes while other observations are going on, so we don't have to contract time on them. And that allows us to do it more inexpensively, and also allows us to search 24 hours a day, 7 days a week. So here's an example of someone using the telescope to look at something called a pulsar. And at the same time they're looking at a pulsar, we can phase the array up or form beams on the sky to conduct a parallel search alongside whatever science program is going on. And we're very, very excited to bring Breakthrough Listen to this next generation set of facilities. So a bit about targets. It seems like every week, sometimes every day, we're hearing about new extrasolar planets that are discovered that are more Earth-like than the previous one. And indeed, there are huge numbers of Earth-like planets that are now known, and eventually we're going to find a planet that is really indistinguishable from the Earth in terms of its size and its chemistry. And when that day comes, that's certainly going to be a very high target for the Breakthrough Listen program. Another interesting thing that's made possible by our discovery of multi-planet systems is an idea called eavesdropping SETI. So if you know that there are 2 planets orbiting another star, or perhaps 3 or 4 or 5, and you know their orbits fairly well, you can actually time your observations of these systems for when the 2 planets are aligned relative to the Earth. So suppose a civilization arises on planet A, and they outgrow their planet, they want some more resources, perhaps like we're thinking of doing with Mars, and they decide to colonize planet B. We would expect that there would be increased communication between those 2 planets, perhaps increased leakage radiation, perhaps radar, something like that between the 2 planets. So if we time our observations for when these are aligned, we have a better chance of intercepting that. And this is something that we're starting to do in the LISTEN program using the multi-planet systems that we know about from other astronomers. Here's another fun idea. This is to look at something called globular clusters. These are very, very dense regions of stars where the stars are much, much closer, much less than a light year, whereas in our nearest star is 5 light years away. Here the nearest stars might be a fraction of a light year away. And there's an idea that comes out of astronomers at Harvard University that these globular clusters might preferentially produce very advanced civilizations, star-faring civilizations, because the stars are so much closer to one another and it's so much easier to get to them. And this is, again, something that we're very, very excited to begin observing in the LISTEN program. How many people have heard about the megastructure star, or Tabby star? Almost as many as SETI at home. That's impressive. About 2 years ago or so, a very interesting star was discovered from the Kepler data set. The Kepler spacecraft is a spacecraft that was dedicated to finding extrasolar planets, and it was fantastically successful at doing that. It found many thousands of extrasolar planets, but it also found this thing, KIC 8462852, kind of an interesting phone number. These are plots of normalized flux, or sort of the amount of light that we receive from the star is maybe a better way of saying that, versus time. So this is basically all of the starlight and then dips from the star, and these are different time scales here showing some of these features. Now, if you look at these and you say, well, those look kind of random and they look pretty deep. This one looks like it goes down to about 17 or 18%. They look kind of strange. That's pretty much what astronomers thought when they looked at these. What we would expect from an extrasolar planet, as evidenced by one of these plots, would be a very regular series of dips as a planet moved between us and the star under Keplerian motion. But of course, what we see here is very random, very stochastic, and also very, very asymmetric. And this caused some astronomers to ask the question, well, what if what's causing this is not a planet, not a natural object, but an artificial object? And there was a number of very outlandish, I guess you might say, but certainly provocative news stories about this. The phrase megastructure was coined, and it spawned a huge amount of activity in the SETI community to search this object to see if perhaps there was other evidence of intelligent life. We looked at it with the LISTEN program. Other astronomers looked at it with other programs. All of the radio and optical SETI that we've done has produced negative results. There's about 25 hours of radio data from the Green Bank telescope that we collected in collaboration with astronomers at Penn State that we're going to be making publicly available, all of the raw data, the lowest level data that we can collect with the telescope. And the announcement of the availability of this data should be made in the next couple of months. So stay tuned for that. And it's a great opportunity for exploring new algorithms. So if in your field of research, if you have an idea for a type of signal that maybe we might be missing, this is a fantastic data set to give that a try on. We also recently had our first scientific results from the LISTEN program published in the Astrophysical Journal. This was work that was led by a PhD student in our group, Emilio Enriquez. He looked at 692 of the stars that we've observed with the Green Bank telescope and processed 180 terabytes of raw data, of filter bank data, and 8 petabytes of raw data. So 8 petabytes came into our systems that resulted in this analysis. 11 candidate signals were identified in this data set, 8 petabytes of raw data, and this is an example of one of these candidate events. So when we use a single-dish radio telescope that can only point at one direction in the sky, we observe stars in what we call an AB-AB cadence. So we observe one star, in this case Hipparcos 4436, followed by a second star, our B star, Hipparcos 3333, and then back to 4436, and likewise for a total of 6 observations. And the reason why we do that is the same reason why Professor David Todd asked the military to turn off the radio transmitters in 1924. We're trying to get rid of terrestrial radio frequency interference. We're trying to get rid of all of the signals that come into our data from our own technology. And what we would expect for a distant technology is that it would only be present when we're pointed at the star that we're observing. If we move the telescope off, the signal should go away. And so sure enough, in this case, the signal went away. So you might be thinking to yourself, well, it's ET, of course, on Hipparcos 4436. But after we analyzed the entire data set, what we discovered is actually we detected this signal, this same transmitter, at other stars. And you can sort of see why that might be, because the signal itself is intermittent. So it's turning on and turning off with some cadence. And in this particular instance, we just got unlucky in that the signal was only on when we were observing on the A star, or 4436, and not on the B stars. But the entire record of all of this analysis, all of the data, all of the events that we recorded, and indeed the scientific publication, is available for download at our website should you want to look into this a little bit more. I promise this is the most complicated slide that I have, but I put it up for a very specific reason, which I'll talk about. So this is a plot on the x-axis, equivalent isotropically radiated power, or luminosity. It's how bright or how powerful a signal is. And then here on the y-axis, this sort of complicated equation, this is basically the rarity of a signal. So how common are our signals and number of stars observed. And then these vertical lines, these represent two different powers of transmitters. So this is the power of the Arecibo planetary radar here, and this is the power of what we would call a Kardashev Type 1 civilization. This is the power of a transmitter that has the energy of all of the sunlight that's falling on planet Earth. Very, very bright transmitter, a transmitter that we actually don't have here on Earth. And so moving to the left in this plot is better because it means that you're more sensitive to weaker signals. And moving down in this plot is better because it means that you're probing rarer signals. It means that you're conducting a more comprehensive search. And all of these data points that you see are searches that have been done in the past. And then here, this is the data point that represents the search that we just published. And this is exactly what we're trying to do in the LISTEN program, is push on this parameter space and conduct comprehensive searches, but describe them very, very accurately so that we know exactly what it is that we have or have not shown with regard to the prevalence of transmitters. So I wanted to move on to just talk about a couple of things that we have detected. It would be kind of a boring talk, I guess, if I just talked about things that we hadn't detected. This is a plot of a very interesting object in astronomy called a fast radio burst, something that's only been known for about the last 10 years. This is the very first one that was discovered by Duncan Lorimer and his colleagues. It was published in Science. And this is a plot of time versus radio frequency. And what you see here is a kind of a curved, it's actually quadratically curved, radio pulse where the higher frequencies arrive earlier than the lower frequencies. And that's actually a very special form of dispersion, a very special property that we see from radio pulses that have transited very, very large distances of interstellar space or even intergalactic space. And the amount of this curve, so how much delayed one frequency is from another frequency, we can actually use as a proxy for its distance. So this pulse was very interesting because it was extraordinarily bright, and the extrapolated distance for how far away this thing was very, very far away. In fact, a billion light years away. And this discovery prompted a whole flurry of activity to try to find more of them. And in fact, a few dozen of these have now been observed, but no one knows what they are. It's really a complete mystery. There are some good guesses. About 90% of astronomers think that it has something to do with a magnetar. This is a highly magnetized neutron star, a dead star, that's maybe rotating very, very quickly. About 9%, let's say 9.9% of astronomers think that it might have something to do with axion stars. This is a hypothetical particle that's a candidate for dark matter. And a few people have even suggested, in fact, a number of very prominent theorists, that maybe that this has something to do with extraterrestrial intelligence. In fact, in particular, a suggestion has been made that this might be some residual from a propulsion system that a very advanced civilization has used. About 3 years ago, a very interesting fast radio burst was discovered that actually repeats. It produces multiple pulses. So all of the other fast radio bursts that have been found only go off one time. We see one pulse and then it's gone. But this one repeats, and it's been given the sort of appropriate name, the repeater. And it was localized, actually, to a small dwarf galaxy about 2.5 billion light years away just in the last several months. So, of course, this very, very interesting object is something that we wanted to explore with the LISTEN program, and indeed we did. We conducted observations of it just a few weeks ago on August 26th, and we detected, the number is now 21. So if you were paying attention to the astronomy press in the last month, maybe you heard the number 15. You're in on the secret. The number's actually 21 now. And we detected all of those pulses in 45 minutes. And this was the highest period of activity that's ever been detected from this source. And we conducted our observations from between 4 and 8 gigahertz in radio frequency, which is also the highest radio frequency that the source has ever been observed at. Now I'm going to get a little bit technical for those that are interested in the audience. This is what's called a spectrogram. So this is a plot of one of the pulses that we observed. And we're actually only able to produce this plot, as you can see, with resolution of less than a millisecond. This plot has a resolution of 10 microseconds because of the power of the breakthrough listen instrumentation. So here's radio frequency and time. And this plot has been corrected for that dispersion that I showed you. So I've subtracted that out. And here I'm zooming in on a little region of that spectrum. And all of the structure that you see here is real and is essentially completely unexplained. No one knows why it looks this way. All of these very sharp cutoffs in time and this spectral structure that you see here, how it has more intensity at some radio frequencies and not others, is also real. And we don't have any idea what this is. Again, we have some ideas, but we're working up a paper on this. So really a very, very fascinating object that we're able to learn about in really very exciting ways using the same instrumentation that we use for our SETI searches. So I wanted to go back just quickly to Project Ozma. This is Frank Drake's original search in 1959, just to contrast it with what we're doing in the LISTEN program. So again, Frank looked at 2 stars. He had a 100 hertz manually tuned channel. With Breakthrough Listen, we're looking at 1 million stars. We can observe 10 billion radio channels instantaneously. And we can observe from 1 to 100 gigahertz at Green Bank for some of our targets. And we've also included an optical component to the search. And I'm really extraordinarily privileged as a scientist and someone involved in this program to point out that Frank's actually a key member of our Breakthrough Listen team. So he's very much involved in what we're doing with the Listen program, and it's really very special to be able to work with Frank. Continuing on that line of thought, I wanted to close with just an observation really about the Drake equation, about really the principal tenet of the search for extraterrestrial intelligence that might not be obvious at first glance. So most of these terms you might guess, the rate of star formation, the fraction of stars that have planets, and the number of Earth-like planets, etc. But there's one here that you might not guess. So imagine that we're sitting here at the Earth, and there are civilizations arising throughout the galaxy, and they exist for some period of time. Maybe they exist for a few thousand years, maybe a few million years. We don't really know. We've only had technology on this planet for about 100 years. And to be perfectly honest, we don't know how much longer we'll have technology. We don't know how much longer we'll exist. There are existential threats, both external and internal, to civilization on this planet. But the question of whether or not we would be able to detect one of these civilizations actually depends not on whether they exist at all, but whether the sphere, the concentric sphere of their radiation, actually exists at the same time that we're looking, which is a different question. And that gives rise to this term, L, the average lifetime of a civilization. And many people believe that in fact the determining factor of N is probably L. The most important thing that's going to determine whether or not we're able to detect another civilization is how long they last. Where might we be in 100 years? If you come to one of the Tennessee Valley Interstellar Workshop events, you might believe that in 100 years we could be traveling certainly between the planets and maybe even between the stars in 100 years. But how about 100,000 years or 1,000,000 years? Could we build giant spaceships, and could we travel the galaxy? Could we even last this long? This is a question that's very, very difficult to answer, but it's a question that SETI is at least able to give us some hint at. Because the civilization, again, that we might eventually communicate with or receive a signal from is so far away from us, we're actually seeing that signal as it was when they initially emitted the signal. So the galaxy is 100,000 light years across. So if we saw a civilization on the other side of the galaxy, we would be seeing that civilization as it was 100,000 years ago. But because we've just recently gained a technological capacity on this planet, it's likely that that other civilization is far more advanced than we are. So in looking at that civilization's past, we might actually be looking at our own future. And this is something that early pioneers in the field of SETI, notably Philip Morrison, called the archaeology of the future, or interstellar archaeology. Thank you.